Okay. So we are now properly going to work on reverse chain rule. And this used to be called recognition. It's weird because it is basically like, or it feels like guesswork. And it kind of is a test of how good is your differentiation so that you can guess it and integrate. Okay, so reverse chain rule. Let's have a look. Now, what we've got is if we're asked, for example, f of x is sine a of x, then we've got to be really careful. If I ask you to integrate this, oh, sorry, there's another one for us to do. Let's give these a try. If I wanted to integrate sine a of x, the first thing I would do is I would say, well, I know how to integrate sine. I actually know that sine comes from minus cos, because cos differentiates to minus sine, so minus cos differentiates to sine. So I kind of half have the answer. I know it involves a minus cos a of x. So I'm going to put that in my answer as almost like a guess. And then I'm going to differentiate it and see how far off I am. So minus cos a of x differentiated by chain rule would actually be a sine a of x. Now I don't want a sine a of x, I just want sine a of x. So I'm out by a factor of 1 over a. That's the adjustment factor I would need to include. So I kind of know the function it's going to come from. I know that sine will come from minus cos. So I know that's going to be part of the answer. So what you could do, some people like doing this, is differentiating minus cos a of x and seeing how far off you are. Because if you're only off by a number, or like a letter in this case, you can adjust it. You can just times by 1 over that thing. So let's look at a similar one here. What do we reckon this is going to come from? This is a 1 over something x. Now, this looks a little bit nastier. And I would also suggest like the denominator is linear, the numerator is a constant. So the numerator is like the derivative of the denominator. The guess here is actually that this is a log. This is ln. So if I asked you to integrate this, and you notice that this is linked to this by its derivative, a linear to a constant, my guess is basically going to be ln of the bottom. Well done if you're confident with this, but I know that this is actually a really tough part of the course. For some people, spotting this is quite hard. So that's part of my answer. That's my guess so far. And then if I differentiate ln of ax plus b, I would get a over ax plus b. That's how you differentiate chain rule the logs. And you don't want a on the top. So it's out by a factor of 1 over a again. And that's your adjustment factor. Okay, so we're going to look at more examples like this. But some people learn this process in lots of different ways. And what it comes from, we're going to look at a much harder one now, or maybe just like a less obvious reverse chain. People think, oh, this just doesn't feel like a formal technique. It is testing your differentiation, if anything. So let's look at the following. If I give you this example, fx equals 2x e to the 2x, e to the x squared. You might think this is by parts, this is substitution, this is hard. How do I do this product of two things? But the product of the two things are linked by their derivative. Because if we look at this sort of operative part here, if you were to differentiate that, it would be a chain rule. And you also know that the kind of inner mechanism x squared, the derivative of x squared is 2x, which pops out. And it does pop out in this case. So actually, my guess for the integral here, if I use capital F of x as the integral, my guess is actually going to be, it's got to be to do with e to the x squared. And if I actually did differentiate e to the x squared, I'd get 2x e to the x squared. So I don't even need to adjust it. The guess is correct. It's all to do with this operative part. if you notice that the other bit is linked to that part by its derivative, you've guessed it straight away. So in a similar way, if I introduce this question here, this is very common, and these a lot of people kind of make a meal of these questions where it's sine and cos to a power, or cos and sine to a power. This again is a little chain, and this is the operative part, because I know sine is like cos is related to cos's derivative. So I'm going to think of this as the main bit that informs my guess. And I'm going to say, I know that the derivative can work out like the derivative of this. So I know that will go to n f dash of x, f of x to the n minus 1. Okay. So what I'm saying is my guess is going to be to do with the cos bit. Now, I know that when you have a cos to a power or something to a power in chain and you differentiate it, the power comes down by 1. So remember with integration, just like in year 12, power it up by 1. So power the guess up by 1. What's going to differentiate to a squared? Something cubed. So my guess is going to be cos cubed. Okay, let's see what happens. So if I want to integrate and get the integral, my guess is going to be cos cubed of x. Now, if I chain rule differentiate that, I would get 3 cos squared x times by the derivative of cos x, which is minus sine x. And so it's 3 times too big, and there's a minus. So the guess needs to be minus a third of the size. Okay, and now don't forget you can still differentiate that and then check it does actually work. So what you've had to do is you've had to like recognize the operative bit of the function. So the e to the x squared was the chain. That's going to inform our guess. Cos to a power, let's power it up by 1 and see how far off we are. Now, I totally appreciate that's still like, this is probably for most people one of the hardest skills in the course, because it requires you to be super confident about everything. And you've got to be like, yeah, I'm kind of keep abreast of all the different things that are going on, then guess it and then adjust it. So this takes a lot of practice. If you feel like you're disproportionately spending time practicing this sort of thing, you're not. It should take up more of your time, and it is harder. So let's do a bit of practice now. I'm going to give you a few minutes, 2 marks each. Try and look up standard integrals, try and see what they link to. Give these a go, and let's have a little look. I think, see if we can tidy these up. They're maybe not as hard as they first look. Okay, so a couple of minutes on these, and then we'll carry on. But yeah, we're doing really, really well. So I'm going to give you 2 minutes thinking time. Okay, so we'll speed on with some of these, check them through. They just look very different in style, but actually the first one really could be tidied up. So don't forget your obvious rules you can do with laws of indices and division and stuff. This one, e to the x to the 2, is actually just e to the 2x. And therefore, you can actually just do this as a subtraction of the powers. So don't forget that that's like a thing we can do. So this is just a really complicated way of asking us to integrate e to the minus x. So that's absolutely fine to work through and give that a go. Now, reverse chain rule, we have to be careful. And it's so easy for something like this to accidentally differentiate it. So just be careful. It's still integration, but we know obviously it will have something to do with e to the minus x. So e to the minus x plus c will be part of your answer. And if you were to differentiate that, e to the minus x, a minus would come down by chain rule. So to compensate, you have to times it by another minus. So that's the main place people will go wrong. Now, it's only one mark, and you might be looking at that thinking, yeah, that's actually quite easy, but it's such an easy place to lose marks with a minus sign. And also to like mistakenly differentiate it, which arguably would still get you very close to the answer here, but you've just got to look out for that minus sign. So then the other bit, the other one that we're dealing with, this one, again, people might look at this and think, is this by parts? Is this some other technique I need to know? But because if we look at, again, the operative bit, which is in red, because the inside of that function's derivative is linked to the other thing, is linked to x, because x squared differentiates to 2x, and that's only away by a number, so like it's quite close to x, you can guess this one. So if we think of this as x squared plus 1 to the half times x, and an x thing would come out if you use that to inform your guess. Okay, so what we would do is we would go, I know that something like this would differ, sorry. I'm guessing something to the half. I'm dealing with that as the operative bit. Okay, so my guess is going to be to power that up. Now, if I power that up by 1, I'd get the 3/2. And that's actually how I would just do it. I would guess x squared plus 1 to the 3/2. You could put the adjustment factor half in already as 2/3. But the key thing is knowing that it's x to the 3/2. So it's x squared plus 1 to the 3/2 is the guess. Now, where we can go from there is that's the guess plus c. And if we have 2x coming out, but we only wanted x coming out, we need to half it as well. So the half and the 2/3 to compensate, which will make 1/3 x squared plus 1 to the 3/2 plus c. Do at this stage still differentiate your answer. You can always differentiate this and check it actually works. Check it actually gets you back to this. If you're confident with chain rule, that will work. Okay. And the way you approach that might have been slightly different, but it's still effectively reverse chain.